Okay, so this is part 2 of topic 15 of waves. So we finished off we just finished off in constructive and deconstructive interference, and we'll kick on now with coherent sources. So the first thing there, guys, is the definition. What are coherent sources? Basically, if you have two sources and the waves from each source come out in phase, or they have a constant phase difference, then they are said to be coherent, okay? And generally they also would have the same frequency, okay? So what is an interference pattern? Okay, so what an interference pattern is, it's the pattern formed when waves from two different sources meet. So when these two waves meet, the waves will interfere with each other, okay, hence interference pattern, and you will get constructive and deconstructive patterns. Now the picture here, there are better pictures online, but I couldn't really get them to come into my notes, fit properly. But this one really, if you can make out what's happening there, you've got all the different crests coming up, okay? So where the C, each line of C is constructive interference, and each D is deconstructive. And the reason is, if you look at the C, right, here, crest meets crest, crest meets crest, crest meets crest, trough, 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 trough. And a deconstructive, we have crest in a trough, crest in a trough, crest in a trough, all the way down. You see? So that's what's happening there, okay? So that's your deconstructive and constructive interference, okay? Polarization. What is polarization? Polarization of waves occurs when the vibrations are confined to one plane only. Key here, only transverse waves can be polarized. Okay, so only transverse waves can be polarized. Longitudinal waves cannot. All right, that's why sound can't be polarized. Sound is a longitudinal wave. Okay, but light can be polarized because light is a transverse wave. Okay, so that's what's happening there. All right, so stationary waves. So what are stationary waves? Stationary waves, when two waves of the same frequency and amplitude moving in opposite directions meet, they interfere with each other, and the resulting wave formed, instead of formed. Apologies, I'll have to edit that. It's a stationary wave. This means there is no transfer of energy. Okay? All right, so basically you get something like this thing here. That's what you get, okay? So two waves are meeting, they're the same frequency and amplitude, but they're going in opposite directions, and that's where you get this kind of pattern here, okay? All right, and there's no transfer of energy. Energy doesn't get transferred from one to the other because they're the exact same, so the energy doesn't transfer, okay? From this, take note of your nodes and your antinodes. Another way to think of a node is no movement, okay? An antinode is anti-node, so node is no movement, so that's the anti of no movement, which means max movement, okay? Your distance from an antinode to an antinode is half a wavelength. From a node to a node is half a wavelength. Therefore, from a node to an antinode is a quarter wavelength. Okay? So what's a full wavelength then? Well, look at it this way. Your wave down and back up going in the same direction. There you go. Okay? That's your wavelength. All right? So this is important because a lot of the questions will come up and they'll just tell you from a node to an antinode, or a node to the corresponding node, or something like that. And they'll give you the lengths of the string, and you're going to have to work back from that. So you have to try and remember, node to node, half a wavelength, antinode to antinode, half a wavelength, node to an antinode, quarter wavelength, antinode to a node, quarter wavelength. That's the way to remember it, okay? And that's all I'm saying here. That's all it's on there on bottom of page 10. Okay. Frequency, the frequency is the same. Yeah, so basically the frequency is the same for all of them. Traveling across it. So problem 5 here. So how many questions do I have? Like 5. All right, so I have one question here really, and then Doppler effect, and then the Doppler effect is kind of the big one really for this chapter. This kind of stuff really plays dividends in the equations for the experiments, the frequency of a stretched string and tension, okay? As well as later on we start looking at wavelengths themselves. But for this topic you kind of just need to know the basics. So a stationary sound wave is set up between a loudspeaker and a wall. The distance between the 4th and the 12th node is 2 meters. Okay, and the speed of sound in air. So we start off with that. C, 340. 340 meters per second. Find the frequencies. All right, okay. And the 4th and the 12th. So 4th to 12th equals 2 meters. Okay, so that's basically 8 nodes. So the distance between 8 nodes is 2 meters. Okay, basically. All right. Find the frequency. So we know C equals F times lambda. So F equals C over lambda. So we have C. We need to find lambda. How are we going to do it? Any ideas? Look at all the information they gave us. They told us that the 4th to the 12th node is 2 meters. Therefore, 8 nodes is 2 meters in length. So how do we find the wavelength from that information? Well, node to node equals lambda over 2. So 8 nodes is going to be, okay, two meters. So node to node is lambda over 2. So 8 nodes in a row is 8 times lambda over 2 equals 2 meters. So that will become 8 lambda equals 4, lambda equals a half. Okay? And then we sub that back up here. So F equals 340 divided by 0.5. F equals 680 hertz. And there you go. Okay? So that's kind of where the information kind of comes in. Stuff like that where they give you enough information to actually solve it. You have to just do a bit of thinking. Okay? You got to kind of work backwards sometimes in these kind of questions. All right. So that's that. We'll come back to more questions like that now in the next topic 16. So the Doppler effect. This is the big one. This is a nice question to get in the exams. They're fairly straightforward. You should be looking to pick up all the marks in these kind of questions. So what is the Doppler effect exactly? Well, it is the apparent change in frequency of a wave due to the relative motion between the source of the wave and the observer. So the apparent change. So in other words, when an ambulance comes towards you, okay, the sound seems to change as it approaches you, and then it changes as it passes you. That's because the sound is moving, and the object that's moving is catching up with the sound. And then when it moves past you, okay, it's moving away from the sound. So that's why you get a higher pitch, I think, usually a higher sounds higher as it comes towards you than as it's going away from you, okay? So basically what you have here, you have 3 waves, 1, 2, 3, okay? The source is in the middle, S, okay? And that's emitting the sound, all right? So the distance, because it's not moving between all the waves, is the same. So we all hear the same sound, just at different times, okay? However, when the source is moving, all right? It's going from B to A, okay? All right? Ahead, think of it this way. Ahead, the crests are closer together than the crests from behind, okay? Wavelength smaller, frequency bigger, okay? So if you remember, C, F times lambda, which means F is inversely proportional to lambda. So therefore, if the wavelength goes down, frequency goes up, and vice versa. If the frequency goes up, the wavelength goes down. Okay, so they're inversely proportional. Behind, the waves are further apart, and this means the wavelength is greater, the frequency drops. Okay, so in an exam, if you're asked to explain this, give the 2 diagrams. Give this diagram first, explain it's not moving, the waves are all the same. Second one, note A to B, state which way it's moving. Say it's going from B to A, or A to B, whichever. Draw the waves like this, where they're, if it's moving towards A, the waves are closer together, and then behind, they're really far apart. Okay? Label it, crest 1, 2, 3, and then just basically give the basic explanation. Okay? All you want to say is, you're saying, well, look, that as it moves from B to A, the wavelengths get smaller, and therefore the sound here frequency gets higher, and as it moves away from B, the wavelengths are larger, therefore the frequency sounds smaller, and that's it. Okay? And that's where you get the symbol here, F dash. All right? Now, and here, if the source, your apparent frequency, appears larger than the actual frequency, it's moving towards you. And if the apparent frequency is less than the actual frequency, it's moving away. All right? So what happens then is in the log tables, the equation you get is F dash equals FC C plus minus U. You have to decide whether it's minus or plus. Okay? Now, the best way to describe this, and to think of it, is as follows. Okay? Distance. If the source is moving towards you, the distance between you and the source is getting smaller, minus, because that's the speed of sound. Okay, because this is the speed of sound minus the speed of the object. Okay, so the object is closing the distance on the sound. It's getting shorter, minus. When it's moving away, the distance is getting larger, plus. All right, so think of it this way. If you find that a bit too complicated, I always say if the easiest way to think of it is, as it's moving towards you, the distance between the object and you is less. So therefore, the distance is minusing each time. It's getting smaller, so we minus. As it moves away from you, the distance between you and the object is getting greater. So therefore, distance increases, plus. Okay? Minus is towards. All right? Okay. All right, so we'll answer a few questions. So I have 2 questions here to do, and then we're done. That's it. A little bit on the Redshift, actually. Okay? All right, so, source of sound of frequency 2 kilohertz is approaching an observer at a speed of 50 meters per second. If the velocity of the sound is 336 meters per second, what is the frequency heard by the observer? Okay, so source of sound. So what we do, as always with these kind of questions, is we write out all the information we have on the left-hand side, okay? So we start here with, now where's my pen? No. So frequency, so they're giving us a frequency. I'm just going to roll this down. So I got a new pen, but the thing is if I touch the screen while writing on the pen, it'll error out. I'm trying to write awkwardly here now. So F equals 2 kilohertz, so 2 by 10 to the 3 hertz. He's approaching an observer. No, observer is not C, U. Speed of sound. So try not to get them all mixed up. I have them listed above here anyway, okay? I forgot to go through with G. F dash, it's a parent frequency. F, actual frequency. C is the speed of sound of the wave. U is the speed of the moving source. Okay? What is the frequency heard? Oh, hang on a minute. The source of sound, yeah, is approaching observer. What is the frequency heard? So we're looking for F dash equals F dash. And approaching the observer. We're approaching the observer, so our distance is getting smaller, minus. Fire in all the information, all your values there, guys, and you should end up getting F dash as 2,349.7 hertz. Okay, 2,349.7 hertz. Okay? All right. Now we get to a more difficult one. Now I'm going to read the question out. I'm then going to roll it up because I need all the space here for this. So a whistle emitting a note of 4 kilohertz is whirled in a horizontal circle of radius 1 meter at a constant speed. If the highest note heard by a person a large distance away is 4,200 hertz. Find, number 1, the speed of the whistle. Number 2, the lowest note heard. Number 3, the time taken for the whistle to make 1 complete revolution. Number 4, the time interval between the person hearing the highest and lowest notes. Speed of sound to be 340. All right, so I'm going to roll this up. You can always reverse the video back to get all the information. All right, so write out everything we just got given. So the whistle emitting a note of 4 kilohertz. So frequency is 4 by 10 to the 3 hertz. Radius of 1 meter. The constant speed. If the highest note heard by a person large distance away, so our parent dash, F dash, equals 40, too many zeros. All right. So find the speed of the whistle. So we're given C as well at the end, was 340. So we're trying to find U. All right. Okay. So we start with that. So number 1, F dash equals FC. C. Now, The whistle is emitting a note of 4 kilohertz, is whirled in a horizontal circle of radius 1 at a constant speed at the highest note heard by a person a large distance away. Is that. Okay, hold up a minute there now. I'm going to draw that out and we explain what's going on here. So we have a circle and we're spinning the whistle. So we'll say A, directly opposite B. And it's spinning this way. That's 1 meter. Okay, so it's spinning around. We're at A. Okay, so we're told that the highest note heard is 4,200 hertz. So therefore, so remember we were saying as the object moves towards you, the wavelength is shorter, the frequency is higher. So therefore we can say highest moving towards. So it's highest moving towards. So therefore F dash FC, if we're moving towards, C minus U. Now we're looking for a U. So there's two ways to do this. Some people like to put in all their values and then rearrange to find U. I like to rearrange first, but a bit of a word of caution here. C minus U. So C minus U. Oh, there, rub that out. That didn't come out right at all. C minus U equals FC over F dash. U minus equals FC over F dash minus C. U equals FC. Hold on a minute, no, I think I did that wrong. So if I multiply across by U and C, C minus U, divide across by F dash, yes, leaving me with C minus U, and then I bring the C over. All right, it should work out. C minus FC over F dash. Okay, so I'm going to fire in my values there now. I shouldn't have moved. I just realized I left my calculator somewhere. There it is. Right, so I'm going to fire in my values just to make definitely sure that works. I think I might have made a mistake there. If I did make a mistake, I'll go back and correct it. So my C value is 340 minus the frequency, which was 4 by 10 to the 3. Times what was C, 340 again, divided by 4,200. Yep, I'm right. Yeah, there we go. I don't know why I thought it was wrong. I'm never wrong, except when I'm wrong. So U equals 16.19. There you go. So we have U. All right, so we have a U value, so we can put that in on our left-hand side then. 16.19 meters per second. So that's the first question answered. Done. Okay. Now, what's the lowest note heard? All right, so if the highest note, so I'm going to have to rub out all my information here, I'm going to rub out just that. So if my highest note is heard as we move towards the object, when am I going to hear my lowest note? Any ideas? The opposite, lowest moving away. So plus. Okay. F dash equals FC, C plus U. Do the other way around. So now we have all our information. We just sub all that in for F dash, and we should end up getting 3818.2 hertz. There you go. Okay, again, give your SI unit. You won't get a mark for the SI, that's part 2 by the way. You won't get marks for giving the SI unit, but if you don't give the SI unit, they take it off, because without the SI unit, what you just gave them means absolutely nothing. All right, so number 3, the time taken for the whistle to make 1 complete revolution. Okay, right, so again, I'm going to rub this out. You can always reverse the video back. So time taken to go all the way around and back on this whistle thing. Right, go all the way back. That's silly. Triangle, displacement, velocity, and time. So basically, we're looking for time. Time equals distance divided by speed. We have speed. It's the speed of the object. Okay. What's our distance? Well, we're moving in a circle. So that's when the circle comes into play. We're moving in a circle. All right, we're going in the circumference of a circle. So therefore, 2 pi r over u. So 2 pi, radius of 1, over 16.19. So our time here should be 0.388 seconds. And that's a decimal point there, not a smudging thing. Okay? All right, so I'm going to rub that out as well because I need the space. Again, you can always rewind the video back. And now the last part. 4. The time interval between the person hearing the highest and the lowest notes. So we assume speed. So we assume the object u is constantly spun at a constant speed, not slowing up or down. We negate all the other factors and simply, so time for 1 we got previously as, not 18. What did I say there? 0.38 seconds. So therefore we just simply, so for half a cycle, there you go. Because we're going from the highest, which is at one of the points, to the lowest, which is directly opposite it. So therefore half the circle, 0.194. And there you go, and that's it. Now your values might be slightly different depending on how you rounded up the figure, some of these figures, okay? So if you rounded up to 3 or 4 decimal places, that's probably where the difference is, so don't worry too much about that, all right? Okay, so the last thing here, this is a common exam paper question. Hasn't been asked in a while, so keep an eye out for it. What exactly is the Doppler effect and the redshift, okay? We use the Doppler effect to calculate the speed of stars, all right? Simply because if a star is moving away from the Earth, okay, all right, the emitted light appears less than it actually is, okay? So if the wavelength is long, we get red, and that's what's called the redshift. That's how they know the universe is still expanding, okay? Because when you look at far distant stars, you get kind of the red hue, which means that the wavelengths we're seeing are longer, which means the universe is still expanding, okay? Which at the moment is a good thing. If we saw the opposite end of the spectrum, where we saw the colors violet or purple, all right, indigo and violet, that means the universe is shrinking. Things are coming towards us. That's bad news, all right? So there you go. That's the purpose of it, is that with the redshift, we can check the speed of stars. If they're moving away from us, they'll give off the red, the color will appear red, okay? All right, because red obviously has a large wavelength. Okay, that's part 2 of waves. Any questions, leave them in the comments below or on the Edmodo page. Up next will be part 15, where we look at all the different wave types, okay?